Recording in progress.
Okay, hopefully this is all clear. The screen is working correctly. Great, okay. So yesterday we spoke a bit about chain complexes and morphisms of chain complexes and their induced maps on homology and things like that. There were like one or two things I wanted to say about chain complexes, starting with chain homotopies. So the name, of course, comes from topology. And so we will have a very similar kind of feeling here. Okay. So these are chain homotopies of chain maps. And the punchline is, well, I will say it, and maybe, it won't be so unexpected. So, okay. A chain map F from C bullet to D bullet is called null homotopic if there are maps. Oh dear. Sn, so indexed by n, from Cn to Dn, or Dn plus 1, yes, such that, okay, I'm going to draw the picture and then I'll write down the relation because I'm not going to get it right. So looks like this. So I have Cn plus 1, then to Cn, this is Dn plus 1, then Dn to Cn minus 1, and so on. And then I have my chain map, which is Fn plus 1. Here it's Fn. Here it's Fn minus 1. These go to Dn plus 1, Dn, Dn minus 1. The right boundary maps here. Differentials. Okay. And now I have my Sn's. These go from Cn to Dn plus 1. So that's Sn. And then this one here will be Sn minus 1. And so I want them to add in a funny way. I want some sort of weird relation. So the relation that I want is that such that, where should I put this? I should move this down a bit. Such that Fn is equal to Dn plus 1, Sn plus Sn minus 1 Dn for all n. It's a weird relation, but this sort of thing crops up naturally in topology. So if you have a continuous map x to y, you can, I don't want to like talk too much about topology here. I want to keep this sort of contained, but there are these, the singular chain complex. There's an induced map on the singular chain complex. And if F is null homotopic, you can produce an Sn that does this. Okay, yeah. The actual punchline is coming later. But yeah. Okay. What else do I want to say? So that's null homotopy. Typically also they write like F is equal to ds plus sd. Suppressing the indices is a very common thing. It makes the proofs easier to look at, which is always nice. Okay. I'm going to change the page. Is that okay? Okay. Yes. Also have Zoom open in case I have. Okay. Okay. And so now I want to compare two maps. Like in topology, I can say that two maps are homotopic to each other. I want to say that two chain maps are chain homotopic to each other. So FG, both are maps from C bullet to D bullet. They are chain homotopic to each other if F minus G is null homotopic. Great. So maybe, I mean, a lot of these definitions are maybe not so surprising, but we should write them down once in our lives. And so, okay, maybe in topology, you've also heard of like a homotopy equivalence. So there's also something you can write down in this setting as well. So if I have F from C bullet to D bullet, this map F is a chain homotopy. What the TOPY equivalence if there exists a map G going the other way, so D bullet to C bullet, such that, oops, such that what? If I compose them, they should be chain homotopic to the appropriate identity chain maps, just like in topology, right? Such that GF and FG are chain homotopic to the appropriate identity chain maps. Great. And so, okay, now what is the point? Maybe less so about this chain homotopy equivalence thing, but like two maps that are chain homotopic induce the same maps on homology. So I'll write this down. If F and G are chain homotopic, then the induced maps on homology agree. So then they induce the same maps on homology. And so this is HN C bullet to HN D bullet. Right, just like in topology, right? Nice. Cool. Okay, I think that was all I wanted to say about chain complexes as a continuation from last time. Okay, and so maybe a brief comment. So far, I've only spoken about homology. You may be wondering, where is the cohomology? It's very similar. It's just flipped in a fun way. So I'll write down homology first, and then I'll write down what cochain complexes look like and the cohomology coming from one. So chain complex. So okay, this is for where is the cohomology? So chain complexes look like this, right? They're descending. So you have D2 going to C1 maybe, and C0. I've just centered everything at 0 just for the sake of the picture. And then D0, and then C minus 1. And we have D minus 1 here, and so on and so forth. And the definition for homology looks like this. So HN is cycles mod boundaries. So ZN mod BN, which is kernel DN mod image DN plus 1, right? And so now, if you flip these things around, you start with something called a cochain complex. You get something similar. So cochain complex, these are ascending indices. So the maps go up. So dot dot dot. I'll have D minus 2. Oh, and the position of the actual index is on the upper part of this of the letter. This is a nice convention, I guess. You might have seen this in topology. So then C minus 1, then this should be D minus 1 going to C0. This is D0 to C1, D1, dot, 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 so on and so forth. So these are ascending. And so now cohomology, which is H superscript N, this is Z superscript N mod this. So these are called cocycles and mod out the co-boundaries. This is kernel dn mod, okay, well, there's only one thing you can put here, down here, and this is image dn minus 1, right? It has to be the map before. Yeah, okay, so it's like the same thing. I'm just going to, well, okay, maybe not today. We won't get to this today, but later when I talk about one of the ext functors, I will say more about this. One of them is contravariant, so this flipping thing will happen, but okay, let's not worry about it. Okay, anything in Zoom? Nothing, okay, good. How am I on time? 15 minutes, great. Okay, so now I will talk about exact functors. So I've explained yesterday what exactness means for two maps, or exactness at a particular node in a chain complex, say. Exact functors are, well, okay, I'll just write them down. So exact functors. So if you start with, let's just define it for, I'll define it for both covariant and contravariant. So an additive functor, let's say for now, contravariant. I'll do that in blue first. An additive functor f from a to b is left or right exact if any short exact sequence 0 to a to b to c to 0 in a, we have, so after you apply f, only part of the sequence remains exact. So, okay, for left exact, it'll look like this. You'll be left with this part, which is fa, fb, and then fc. And if it's right exact, you're left with fa, fb, fc, and 0 on the right. So is exact. Okay, and then if it's, or sorry, not contravariant, my bad. This is meant to be covariant. Yes. Now for contravariant, I'll do it in red. It's like the same. You just have to flip things around. So you'll get 0 to fc, fb, fa. So just, again, just the left part, right? And then fc, fb, fa 0. Okay. And then if I just call a functor exact, what does that mean? It means they're both, it's both left and right exact at the same time. So you get both zeros in the beginning and the end. So f is exact if it is both left and right exact. Nice. And so probably for this week, maybe even part of next week, the only functors we will talk about, like actual ones we know about, are the following. So we have the covariant Hom functor. So let's just stick to our modules, but you know, in general, there's a Hom functor. So this is the covariant Hom functor. And then there's another one, right? Because Hom has two parts. What if I fix the other one, other component? So then that's Hom dash m. this is a contravariant. And then the other one I want to talk about, which I won't talk about today, but there's another one, which is the tensor product. There's also the other one, but it's like there's a symmetry that is there, so I'm not going to bother. This is tensor product. So, I mean, tensor product, so in RMOD, right? This, you'd have to have a tensor product in your category if you wanted to do this, but I'm not going to talk about that. So let's just think about R modules. So which of these are left exact? Which of these are right exact? Well, I won't prove them. You should check for yourself. This one is left exact. This one is also left exact. Oops. Whoa. Left exact. And the tensor product is right exact. So, okay, maybe I'll focus on this one for today, the covariant Hom functor. So nothing too crazy. I don't want to have to deal with flipping things in my head all the time. Right. So if I start with a short exact sequence 0, A, B, C, 0, then right because it's left exact, if I apply F and take out what I know to be exact, I will get 0 hom MA to hom MB to hom MC. And I don't know for sure if I can, like, I mean, I can of course put a 0 here, but now I don't know if the resulting sequence is exact, so I'm just gonna not write that down. I know for sure that this sequence is exact, but you might ask like a few questions, right? Like when is this functor exact? Or maybe in general, like, the definition is written that like, oh, for all short exact sequences, I need this functor to be exact. Maybe you might ask like, oh, maybe is there a smaller collection of short exact sequences? There's a cheap answer for that. So I'll probably talk about that one first. But the first question about whether, more specifically, I should say, like, if I can choose M carefully so that this functor is exact, that has a very interesting answer, which we are first going to answer very tautologically, but we will, in the next day and the day after, we will see it's a little more interesting. Okay. Let me just check the Zoom. Good. Okay. And I guess another related point is like, okay, if I've chosen M, like in the generic case, I guess. Okay, maybe I shouldn't say generic case. I actually don't know if it is generic. If I pick a random module, it's probably not going to be, most of the time they aren't. In that case, like, is there something I can put here and still preserve exactness? There are lots of questions. So next time we will talk about this. Okay. So now a slight detour into adjoint pairs and exactness, because at least two of the functors that I've written before they form an adjoint pair. So I should probably say something about adjoint pairs and exactness. I'm not going to be using most of these results. This is just as a curiosity. It's nice to know. So if L going from A to B and R going from B to A are an adjoint, they form an adjoint pair of additive functors, then, okay, maybe, I don't know, maybe if everyone here went to Mark's course last time, I'll just write down what it means. So that is, at least succinctly, i.e. there exists a natural isomorphism. And this time there is a very particular meaning for this natural isomorphism. So this is between hom and B of LA and B. Okay, and then this one is naturally isomorphic to the hom set in A R B. So adjoint because analysis, right? Okay, fun. Yeah, so this is the case then. Because we're working with abelian categories, this isomorphism is an abelian group isomorphism, blah, blah, blah. Okay, the consequence is that L is right exact. And then R is left exact. Don't get those two mixed up. I know. So, right, the example above, I mean, there's the classic tensor Hom adjunction, right? So this one is the L, and then the Hom is the R. So this particular Hom. And you might have seen the usual tensor Hom adjunction, just replace L and R with these, and very nice. So, okay, now we already know, we've corroborated this in a different way, I guess. You can check it by hand, or, maybe you know something about this. Okay, cool. Okay, a little bit more about these adjoint pairs. So there's a result. So I mean, okay, maybe I want to say something about why this should be true. So one ingredient you need in order to prove this result is this some kind of Yoneda lemma. They call it a Yoneda lemma. It looks a little different. I mean, it's posed in this world of homological algebra. So so the Yoneda embedding in this situation is A is sent to the Hom functor, the contravariant one. Hom A, this one. And so this thing, this functor, I didn't describe what it does to maps, but it's the, what is it, pre-composition? Yeah. Yeah. This functor reflects exactness. And I will explain what that means. That is to say, so i.e., if we have exactness at a particular node, so if I have, if A, B, C, so the maps here, F and G, is if I have exactness here, so, or sorry,
Maybe it's a minor nitpicky thing. So you have it's Hom sub A, but you also have it's sending to A. So
Oh.
I'm thinking like it's an object. What's inside the Hom whatever thing is an object of A.
Yeah, this is bad. My handwriting sucks. This A is an object of the script A.
Okay.
Yeah. My bad.
And what's the category on the right?
The category on the right is this one here. It's A, B, and then curly A op. These are the contravariant functors from A to abelian groups. And the morphisms are natural transformations. I'm not going to talk about this. I think one of Mark's recordings should have this. Okay.
What exactly should we have?
So the Yoneda embedding, this one.
Yeah. We talked about Yoneda for sets, but not for groups. But it's actually a pretty easy extension.
Nice, no problems. That's good. Yeah. So I'm outlining some kind of Yoneda. I mean, it's called the Yoneda lemma in the text that I was reading. It's supposed to be very similar. And in this particular case, there's this. So the result is that this functor, this Yoneda embedding, reflects exactness in this particular way. So if I have so the result is that this sequence is exact if, so now for all m in curly a, script a, the following happens. Hum curly a, m a, and then f lower star, m b, and then this should be g lower star, and then hum a, m c. If this is exact. So that's cool. And I might as well complete the proof if we are willing to accept this fact. So the proof that, oh, sure, yes, yeah. Yeah, no problem. Yeah, no worries. Let me, if you need anything, let me know. I'm happy to yeah. That's good. All good? Great. So yeah, just to sketch the proof of why adjoint pairs have this nice exactness property, I'll just do like half of it, and the other half is like a flipped version of this proof. It's like the same, so I'm not going to bother. So if I take any short exact sequence, I'm going to use X, Y, and Z this time because now I have A's and B's floating around and L's and R's. So I take this in B. Okay, so this is a short exact sequence in B. Then, so now I can form, I can apply one of the hum functors, right? I can do 0 to hum B LAX. Then that goes to hum B LAY. Then this goes to hum B LAZ. And so and this row is exact because hum is left exact. Okay, and now I have these natural isomorphisms with the flip-flopped the adjoint thing. So I get these isomorphisms. Now I put hum A and then A Rx, and then again hum A. Oh, I need to really distinguish these A's. A and then RY, and then A RZ. And I can also put 0 here too. This naturality condition tells you now that this all commutes. Okay, and because of that, the bottom row is also exact. So this row is exact. And then as a result of the naturality squares, this row is also exact. And now I have to use the Yoneda result. Because I've chosen, what do I can choose A arbitrarily here. This bottom row, I can conclude from the bottom row for any A using Yoneda that 0 Rx, Ry, Rz is exact. So R is left exact. And then there's a there's a like an op proof. You do everything in the opposite category if you want to prove the result for the L. Okay. No problem. So this is cool. Category theory is great. Okay, so now let's get back to the real world, I guess. Maybe this is the real world, and I'm just playing with particular functors to get a grip on it. I don't know, philosophy. Okay, we'll look at a particular functor. I want to go back to the hom functor I mentioned, and back to our modules. So hom m dash. So there were these questions that I had earlier, right? Like, which m makes this functor exact? And then I mentioned there was a cheap answer to the second question, which is like, you know, maybe it's possible that some short exact sequences are preserved, even if I pick a random m. The cheap answer is that because I'm working with an additive functor, there are actually these nice enough short exact sequences for which additive functors are just exact on. And they're called the split exact ones. Okay, so split exact sequences are not important because of this, that they're more important for other reasons that I won't get to today, but this is like a cheap answer. So maybe depending on time, yeah, I can talk about them. I'll write down what a split exact sequence is, just for your information. So split SES or split exact. Well, okay, they were already exact, but so split exact SES. So it's a short exact sequence as usual, A, B, C, 0. I have maps F and G here. But there are a few conditions that are just equivalent. I will just write them down. Such that. So there are, yeah, 3 things that I want. One is that there is a section S going this way, for which, so what is the section supposed to do? GS, so we do S first and then G. That's equal to it's C. The other one is I can have a retract R. What a retract supposed to do, such that RF is equal to, so F first, right? So then id A. And then the last equivalent. So, okay. So I should write these are equivalent. The last condition is that, so this is a chain complex, right? So the last condition is that there's this chain complex, this split exact short exact sequence is isomorphic to the following. So the complex is isomorphic to the following complex: 0, A O plus C, C 0, and the maps here are the canonical ones. They're the I1 and the P2. So remember, what is this supposed to look like? This is to say, so if I write 0, A, B, C, wait, yeah, make this longer. 0. In particular, it should be like this. You can have identity here, and then something here, and these all have to commute, right? Because these are morphisms of complexes. Okay, cool. So punchline was that, so the fact or the punchline is that additive functors preserve split exact sequences. Split exact short exact sequence. Maybe I don't need the second exact. I forget. Split. So that is to say, if I apply F it will give me the full thing. That is 0 FA, FB, FC, 0 is exact. That's fun. I mean, it's a little cheap. Not super interesting. It's just a consequence of additivity. Okay. More interesting question. Yes. Oh, up. Yes. No worries. Mhm. Zoom. No. Cool. So I can choose M carefully, possibly, in a way that the covariant Hom functor is exact. And we have a name for these particular modules. So they're called projective modules. And in a abelian category in general, you would call this a projective object. I'm going to stick with modules because what I'm about to say, some characterizations for projectiveness will depend, or like the examples that I have in mind are all in RMod. So that's, yeah. So projective modules are those, projective modules P are those for which P dash is an exact functor. Okay. And so what is it? What is a different way to, or I guess, what is the definition? This is, I mean, you can say this, but this doesn't really help me think about them. So projective modules are characterized by a lifting property. Lifting property. That is, for any surjection B to C. So I'll call this G, since that's what we usually do. And any map P to C, I'll call it gamma. There exists a lift beta going from P to B, so that I'll draw a diagram, but the diagram will end up commuting. It's that gamma is equal to G beta. So maybe I'll draw it here in red. Maybe. So P can go here. I have gamma, then C. Then I like to write a 0 in, so I don't know, it's familiarity with this. This row is exact, so exact. And this is G. I can form a lift. So a lift, right? They're not unique, so there could be other ones. And there's a beta that makes this commute. Great. And I'm not going to talk about this today, but there is like a, I don't want to say opposite, I don't know what the right word is, but there's like a related kind of module called an injective module that we will talk about tomorrow.
Is
Which-
it a dual notion?
Dual? Yeah, okay, good. Dual. I don't want to like use words that are reserved for something, Yeah, dual, good. I trust Mark, so I will call it a dual notion, injective modules. So we'll talk about that tomorrow. But today I just want to introduce projective stuff and say some things. Yeah. So this is what projective modules are. And you might ask, okay, are there any projective R modules? Yes. There are the free modules. And I'll just like sketch how you can see this. So I like to write F for free module. So if I have F here and then a C, and then I write down a surjection G like this, maybe this should be gamma. What I can do is, so F is free, so it has like it's just the R linear span of some basis. Look at where that basis goes under gamma. So you have just a list of elements in C. Once you do that, G is surjective. Just for every element of C in that list that we've produced, look at one of its preimages. Just pick one. And then define a new map beta that sends each generator of F to that particular choice of preimage that we've done. And you can check that it, extend by linearity, blah, blah, blah. It will work out. So free modules are good. I'm not going to write out the details. This is not bad. Okay. So next natural example is, okay, direct summands of free modules. That is to say, if I have P O plus Q, and maybe I call it F. If P O plus Q it ends up being a free module over R, then P and Q are projective. And so, okay, what's the picture I could draw for this? I'll just do it for P, the same proof for Q, right? So again, B, C, 0, P goes here. So P, naturally, you get this canonical inclusion into F, into P O plus Q, right? So there's a map going this way to F. Oh, maybe I should make more space. I'll do it this way. Vertically, maybe. So there's a map going, P includes into F, so this way. F also projects down to P, so there's the I and there's the P. These are just the ones coming from the coproduct. And so F is free, so if I trace down P and gamma here, so gamma P is a map, so I can lift that map along G, and I can get something else here. Let's call it B tilde, beta tilde. How should I then make a map from P to P? Well, I have to chase it along some way. I do I and then beta tilde maybe. And you can check that will work. Try I beta tilde. That will work. Okay. Great. And so, okay, maybe another fun fact, maybe important fact is that so direct summands of free modules are projective modules. The converse is also true. Every projective module is a direct summand of some free module. How do you see this? So we showed one way. Other way is if A is projective, look at the free module generated by the elements in A, or generated by the set. So Mark talked about these free and forgetful, probably. This is that. Look at F of A. This is the usual notation. So look at F of A, and so you're given the surjection to A. And then there's the identity map from A to A. Pull this back, or lift it. And so then you end up just getting a section and a little bit more, and you say a little bit more, and then that's it. A appears as a as a summand of f of a. I won't talk more about this, but yeah. Okay, cool. So we have a few, we have quite a few actually, quite a few projective modules. And it actually turns out that, you know, in a lot of cases, if you choose your R correctly, which is often the case, so if R is equal to Z or a field, apparently even a division ring, which I actually never done this before. Maybe I have, I don't remember, but it turns out that projective modules end up just being free anyways. So that happens, that's cool, but this is not always the case. So, okay, so I should write this down. These settings, projective R modules end up being free anyways. Oh my gosh. Okay, and so when we should say something about when a projective module is not a free module. So maybe one way to spin out examples is to take your ring as a product of rings. So maybe my R is just R1 times R2, and then I can take my projective module to just be R1 times 0 over this R, or just 0 times R2. So these two, they sum to R, right? In R mod. And so since they sum to, so the direct sum, right? Direct sum. Since they direct sum to R, each of these choices for P are projective, but they're not free because I can have 0, 1, and I can act down anything in this, and I'll get 0. So you get this weird relation. This should not happen. So P is not free. Either choice, I mean. You just flip it around. Oh, did the screen? Oh, okay.
There's a piece of.
Oh, okay.
Is this a common problem?
I think it's because the timer, like 45 minutes or something.
Your time zones,
No.
Averaging out analysis.
That's like the 10-minute warning, I guess. That's good. Okay.
Yeah, I'm surprised like it doesn't have those sometimes. I guess now it's let's use
we more time.
more PowerPoints.
Right.
We just, oh, that's gotta be it.
Okay.
Weird, you think the topologist would.
Wait, so explain to me again why that thing isn't free. I can't really read what you.
Oh, my bad. This, I can always write down something like this. So I can take the element 0, 1 in R and scalar multiply something like, so if I take the first choice for P in R1 times 0, I can do like this. And then I'll get 0 comma 0, right? That means it's not free.
Oh, okay.
Yeah, this should not happen if it's free. Okay. P not free. Okay. Maybe a concrete example. So if my R is equal to Z mod 60, this is the usual, you use your remainder theorem, and Z mod 2Z times Z mod 3Z. This very concrete example. Okay. So this is so maybe another thing I could say is like, oh, maybe I look at just the finite abelian groups, the finite Z modules. They only have one projective module, which is 0. That's silly. So this is all just to say projective modules and free modules don't have torsion. Okay, fine. That is something good to know.
Don't have what?
They don't have torsion. They're torsion free. Projective modules are torsion free. Fact. Okay. So I've defined projective modules. Now the question is, is hum p dash exact? Yes, sort of by definition. And I have like 5 minutes, so maybe I won't say this. It's literally like we've defined projective modules to be the ones so that the covariant hum functor is exact. It's not a hard proof, so I won't write it down. But you might object like, oh, this is stupid. Why would you? I mean, you've defined an object that. I mean, you've asked a question. You define an object that does the thing you want it to do. Is there a way to, if I go on the street and I say hello to my nearest module, is it projective? There's got to be a better way to check than to do all this. This is like a lot. And this is where Ext comes in. So there's something we can calculate. It's called an Ext group. Or there are multiple the higher Ext groups, we can calculate them. And there's a characterization of them. So I'll just write down this result and I'll write down Ext, and that's tomorrow's topic. Tomorrow's topic is how to calculate Ext. So my result, the following are equivalent to each other. 1, A is projective, is a projective module. 2, so this equivalence we saw hum A dash is exact. The third one is that these Ext groups, Ext I, and then A, B is, so I say equal to 0 for all I bigger than or equal to 1 and all B. So we'll learn how to calculate these. But this still might look bad. It's like, oh my goodness, there's a lot of X groups to calculate. You just need to only calculate the first one, or the 1th one. There's a 0th one. Okay. The first is the 0th one. Okay, whatever. X1 A B equal to 0 for all B. Okay, so this is a nice result. Whatever this X group is, I'll talk about this tomorrow, how to actually calculate it. But this is nice. This is like this 4th criteria in particular is like, okay, something you might be able to do if there's a nice way to calculate X. That's not like silly. So that's tomorrow. And since I have a minute, here's a fun fact. So shout out to adjoint pairs again. So if I have LR adjoint pair of additive functors, if R is actually exact, if you know that R is exact, then L preserves projectives. And then, so that is to say, if you start with a projective object, then LP is also projective. And then on the flip side, the dual side, I guess, if L is exact, then R preserves injectives, which, I haven't talked about, but that's tomorrow. Fun fact. Okay, I will see you on Wednesday. Oh, question, yes.
So there actually are situations where it's practical to show something's projective by showing up its X ones against every other module is 0.
Oh, wait, can you repeat the question? So are you asking if?
So you said that's like, you said the theorem was to get better conditions for proving something's projective.
Yeah, this 4th condition in particular is like nice because it's just the calculation of one group, which will end up just being taking cohomology. I just need to calculate one kernel, one image, and just take the quotient. And so that's hopefully not too bad. You can ask a computer to do this. Macaulay 2 is a wonderful program. I love it.
Even though it ranges over all possible b.
Oh, sure. Yeah, that's the other. Okay, yes, that is a fair objection.
Yeah, but it's easier to check than 2. That also
Yeah,
makes
yeah.
Overall be.
Yeah, this is certainly, yeah, it's certainly still like, yeah, you're right. But maybe, one thing we can say is like maybe we have results about how X sort of decomposes if in the second component you can maybe decompose the second component into like factors or something. Maybe there's a way. So I will talk about that. That's a good question. Yeah. So I mean, yes, still good objection. It's still hard, but there are still ways to break this down. So in abelian groups, for example, abelian group, finitely generated abelian groups have a nice decomposition. We will use this. Yeah. So it's not that bad. Okay. How's the Zoom? Yeah, okay, thank you for coming. I'll stop recording.
And I have a question.
Oh, yes.
So we talked about this characterization of projective modules, like either Hom is exact, or you could say it has a lifting thing, or it's like a direct sum of the free module. Does all of this carry over to just like the general abelian category setting? Like if you talk about projective objects, can you say like they're projective if and only if they're direct sums of free objects? I don't know if that is a well-defined thing that I just said.
Actually, that's a good question. I have to check. I mean, yeah, coproducts exist in abelian category, so this is not, so that probably the case that, yeah, I mean, nothing that I did here in this depended on module facts.
Well, the free stuff does.
The free, oh, I see. Yeah, you need to be able to make this free thing happen.
Maybe if you have that, then maybe you're good at it.
I don't know. Mark, yeah.
I think that you're right. Well,
If you have a left adjoint to the forgetful, then
yeah.
Yeah.
Except what even would the forgetful functor be?
What are you
Arbitrary,
forgetting to? Yeah.
in an arbitrary abelian category.
Yeah, what are you
Okay,
forgetting?
how about it also
Yeah.
has sets?
I think you need the forgetful functor to be exact in the sense of preserving like surjection or preserving epimorphisms, and then you need to have a left adjoint. And then you can make a similar argument to say that the left adjoint preserves projectives. So it takes projective sets to projective objects, and every set is projective according to the axiom of choice.
Mhm.
Yeah. Good talk.
Thanks. See you tomorrow.
Thank you.